And then when the video finishes, Ted finishes up the entire presentation with a quick summary.
And Ted,
don't you think that's part of the...
And thank you for joining us today. This is a joint webinar with the Northeast ESD chapter, IEEE, SMTA, and IMAPS. It was originally planned to be an in-person meeting, and we had to cancel it because of the COVID-19 situation. So I offered to host it and share it with the members through this webinar. Now, we're going to be seeing some very interesting information, new methods of measuring ionization with sensitivities in the Class 0 region. As you see here, John Glenn is the presenter. Good man. I've known him for years. And he is the Director of Sales, Marketing, and Product Development for NRD. He has been the driving force behind the development of this new technology. And in a moment, I'll turn it over to him. Before I do that, just very briefly, I wanted to, some of you are new, and I wanted to introduce you to my company. This is a company we formed several years ago, and we have a consulting group with focus on professional sales only, services, I should say, and no product sales. So that's an important distinction. And I also wanted to share with you that we have some complementary training available. And I'm going to switch now to my website to make sure that I'll take a quick tour through it. Susan, can you see that? I just wanted to verify.
Yes.
Okay,
Yep.
good. Last time it didn't switch over for whatever reason. Anyway, this is our website, and there's a good deal of complementary information and training opportunities. Under this segment is a list of videos, short training segments, 5 minutes typically, on some very important technical topics. So you'd be well advised to look at them, and demonstrations I think you'll find very revealing. The other thing is we have complimentary webinars that we show throughout the year, and I would encourage you to go there to this recorded webinar section. And then, let's see, what else can I tell you? There's remote support, there are upcoming training sessions here, but that's the gist of it. So now with that, I'm going to turn it back over to John and stop my sharing so that John can take over.
Where's the...
Bottom center, bottom right green share screen.
Oh, I've got that, but where's the... Is it here? No. Thanks, Ted. I appreciate the opportunity to present what we consider a real exciting technology, and I want to welcome everybody for joining us on this webinar today. And I want to run through, I think some showed this off too over time, but what is a really new and exciting technology for measuring ionization performance. This is a picture of what the initial product device is going to look like. And basically it's designed for much more sensitive applications than what a charge plate has been able to deliver. And now I can't move the screen.
Back on.
So the outline briefly is to talk a little bit about device sensitivity, what's happening in the semiconductor world, give a brief overview of the current technology that's available, the charge plate monitor that's been in use for the last 35, 40 years, and the new measurement technology, IonMaster, that we're going to be discussing today. We'll deal with some questions that you might have and a quick summary at the end in terms of why we think this is such a valuable tool going forward. So device sensitivity. We're talking about this with customers for quite a while. Those that are in the disk drive industry are well aware of how sensitive their product is to any kind of voltage static charge on the surface, and their sensitivities have gone all the way down to 20 volt for human body model and 5 volt for charge device model, and going lower. In the semiconductor world, as we watch geometries continue to shrink, we're looking at them dropping from 14 or 28 nanometers. The new processes are going into production now at 10 nanometers. And the sensitivity that's occurring there is going to be equivalent to what you're seeing in the disk drive world. But what does that mean to those that are using ionizers to enhance their manufacturing processes? Well, it's going to require ionizers to maintain offset voltages of probably better than 5 volts. And we're going to need to be able to measure these things. And what currently is out there, and when you measure offset measurements, it's not the same when you just stick a charge plate underneath a certain environment. That's not the same as what you would see in an MR head, and it's not going to be the same thing that you're seeing in an IC. Charge plate initially was kind of developed to emulate what, a large wafer used to look like. So when we talk about device sensitivity continuing, semiconductor processes are ramping up 5 nanometer processes now in development later this year using FinFET technology. And they're also eyeing gate-all-around for the move to 2 to 3 nanometers. Basically, these are next generation geometries that are going to be used in developing semiconductor processes going forward. TSMC already has a risk production line at the 3 nanometer level for FinFET, and they expect to have that running in the second half of this year. Now, whether fabs continue with FinFET at 3 nanometers or gate-all-around, the sensitivity of devices exposed to static charge will continue to track lower. And I think that's fairly obvious. If you look at any of the charts from the semiconductor monitoring methodologies in terms of processes and static charge issues, it continues to trend lower and getting incredibly sensitive. So in today's world, measurement technology is pretty much centered around the charge plate monitor, and it's been a tool that's been used to evaluate ionization performance for almost 40 years. And it has been a very effective tool for analyzing ionizers up until recently. Severe shortcomings now that the ESD 2020 has an offset requirement of 35 volts, which electrical ionizers will struggle to meet without a feedback mechanism. And in the past, one needs to understand that integrated circuits had capacitance built into them, had diode protection built into them, so that they were somewhat immune to serious ESD charges on the surfaces. As these geometries continue to shrink, those protections that are in the die are now being eliminated, making the die that much more sensitive. Does that translate into the die going into packaged products? Well, of course it does. Going back to the charge plate monitor, the CPM basically consists of a conductive plate that's isolated from the environment. It's a device to measure contactless the potential on the plate with respect to ground. So basically, there's no contact to the plate to discharge it. This is the ionizer sending ions to the plate and allowing it to show how long it takes to discharge a certain number. And typically that number is 1,000 volts, and you start a clock, you take that 1,000 volts and you run it down to 100 volts, and that gives you a measurement on how well the ionizer is performing. As soon as the ion stream hits the plate, the charge plate monitor, the voltage drops, and there's usually a timer built into the charge plate monitor that will give you the time frame in terms of how that occurs. So what are the CPM strengths? Well, the CPM of the charge plate monitor has been the de facto standard for ionization test method ANSI/ESD 3.1 for probably a good 30 years. The ionization defines the test methods and instrumentation for making discharge measurements of air ionization equipment in defined environments. Basically, neutralizing static charge on surfaces is the ionizer doing its job. And the STM stands for Standard Test Method 3.1, so they run through basically a procedure on how you would evaluate the charge plate in your ionizer and how it's performing. It's fairly well defined in the standard. So what are some of the shortcomings, however, on a charge plate? Well, one of the shortcomings is it's much too large to fit into a lot of mini environments and tool load-unload stations in many modern applications, and whether that be contract manufacturing with package devices or whether it's an environment in semiconductor back end, there's not a lot of space, to put a full-blown charge plate in to evaluate how the ionizer is performing. Equally bad in those environments, it causes electrostatic effects on the tight confines by supplying a large amount of grounded surface. So again, you're not getting the performance characteristics of what the ionizer is doing in that environment. So to deal with the problems of it being too large, remote plates are an alternative, but they produce extremely long discharge times due to the parasitic capacitance of the wire connecting to the plate. Other instruments employ smaller plates and use a circuit to degenerate the capacitance of the wire, so you get a little bit better understanding of what's happening. But the issue with that is that the discharge performance characteristics don't correspond with what a CPM typically would see. Now we'll get into a little bit of the environment that we're focused on and some of the real concerns going forward. Class 0 is defined with 200-volt human body model, 100-volt charge device model back in 2010, give or take. Well, is that really a relevant methodology for analyzing how good your ionizers are performing in the more sensitive environments of today? Today, failure voltages are much less than 100 volts, and ionizing switching voltages in the current standard are at 35, and I would expect that to trend lower. Because what's coming next, we're looking at 20-volt HBM and 5-volt CDM sensitivities, and even that could be heading lower in the not-too-distant future. And so what's available today to meet these new sensitivities? How can I actually ascertain what's going on in my environment to make sure that my parts aren't getting charged up and I'm dealing with latent failures downstream? So what we thought about and came up with was a new idea to measure how ionizers are performing. And we basically are not putting a charge on the surface. We're measuring the ion current and density to ascertain how many ions are being addressed to a certain surface environment, looking at the balance of both positive and negative ions, and ascertaining how quickly that combination is discharging that static charge on the surface. So we look at the balance and discharge paths, and similar to what a charge plate does today, but we were a lot more sensitive than what a charge plate is. And I think that that's going to be a real benefit evaluating how ionizers are performing in the future, as we can be a lot more accurate at lower voltages. One of the issues that come into play is settling time, with a low charge density of ions, or the number of ions being addressed to discharge the surface material. You'll have a very long settling time with a CPM in terms of ascertaining how quickly you're getting that surface discharged. IonMaster can sense that and get a discharge performance reading to you a lot quicker and let you know what's happening in that environment. And factors in settling time that come into play are what is the starting voltage, what's the ending voltage, and what's the ion density. And that's something a charge, be clear, a charge plate does not do that. Doesn't measure charge density or current. It just, the ions hit the plate, it's got a voltage charge, and it just measures the ions that it draws in to show the discharge performance down to 100 volts. So here's a quick graphical description of starting at a certain voltage and the discharge curve that you'll see, and what the settling time is in terms of getting down to as close to zero, which is the goal. How quickly a charge plate would get there, and how quickly our sensor will get to that same point in analyzing what the performance characteristics are from the ionizer. Spatial resolution, it's a couple of different formats in terms of ions coming into an environment and measuring how they're impacting surface environments. The typical charge plate is a 6-inch by 6-inch plate with the ion concentration. The CPM picks up an average over a large area, which is fine. Smaller areas equate to better spatial resolution, i.e. there's more ions hitting a small plate, which is located where you want to analyze what's going on. In IronMaster, it's a 3-inch squared kind of configuration inside of the sensor, And then there are smaller external plates that are used that are 1 inch by 1 inch squared to measure performance characteristics of ionizers. There's a physical photograph of a charge plate on the left-hand side and the monitor on the right, which handles all the electronics involved in measuring the performance. There's what an external charge plate configuration would look like. What's interesting here is you'll get faster decay times because they're usually positioned in a higher concentration of airflow. But the parasitic capacitance caused by the reading may not necessarily correlate to what the CPM is seeing. So you can stick that close or closer to an ion airflow in the environment where it's happening. So you'll see pretty quick, discharge times, or you should, but unfortunately, the cabling to it, unless you've got some electronics to correlate back to the CPM, will be problematic. Then there's Ionmaster, which we've been working on for quite some time now, where we use a plus or minus 30 volt electric field to draw the ions in. We measure the positive, we measure the negative and the balance at the same time, and report the results in real time. So in a charge plate, normally you're just measuring each one of those characteristics one at a time. Here we measure all three at the same time. Temporal resolution. Here is decay time is an indirect way of measuring charge density. The sensor has a 1 second sampling rate, and we can adjust that if we needed to. It allows us to pick up more of the ripple emanating from the ionization source. I consider this next slide to be one of the more critical considerations when it comes to evaluating ionizers and how they're performing. Here we're taking a typical decay time from 1,000 to 100 volts. And the slope changes over time as the amount of ions being drawn into the charge plate slows down as the voltage on the charge plate itself drops. But we take a small subsection of that decay slope and do a quick analysis. Well, what's really going on inside of that slope? And what you see is some fairly significant variations that are averaged out in the algorithm that a charge plate would use. But you'll see potentially all the way down minus 30 or 40 volts and a plus 50, 60, or 70 volts during the course of the decay performance. And that can be very problematic downstream in terms of having an impact on highly sensitive devices. So what are people doing today to get ionizers to perform correctly in these next generation highly sensitive environments? Well, monitoring current and voltage is one methodology where you take a look at how much current is going into the ionizer and look at the variations in the voltage and keep those under tight control to make sure that the ionizer itself isn't drifting too badly. You can put a faceplate. There is faceplates on fan grids of ionizers that are used for a feedback mechanism back into the input of the ionizer itself. You can get a little bit closer to what's actually happening in the world of where the ionization is performing by using a 1 inch squared remote charge plate and feeding that data back. All of these have drawbacks when you're trying to really get close to understanding in highly sensitive environments how good your ionizer is working and how accurate it is in terms of holding its balance and performing the way you need it to. Which is why we come up with the last solution, Ionmaster, which incorporates all those critical elements of letting you know exactly what's going on in the area that you need to know what's going on. Some other future things we plan on adding to the solution that we currently have in Ionmaster is measuring swing voltage. And this is important because as you're measuring ionizers and as they're being pushed out sometimes just with high frequency or pulsed technologies, it all sounds fine, and you see better performance characteristics as you get ions into the air farther downstream. But what you don't see is the electrical field that can cause some severe impairments on electronic components if the field is too great. And as devices become more sensitive, the higher the swing voltage, the greater the field, the more potential problematic issues you may have with highly sensitive components. And the other element that we want to evaluate as well is frequency. How rapidly are you pushing both positive and negative ions out? It becomes very problematic for a lot of ion sensing technology because static charge doesn't dissipate instantaneously. The charge plate operates generally between 1 and 10 hertz. And so if you have a high frequency ionizer pushing out positive and negative ions, you may have a significant swing voltage or offset voltage. And you may not be aware that you're causing more harm than really helping in terms of discharging static on the surface. That may look fine, but the field that's being created is, can be very problematic. So it's important to keep some of those concepts in mind when it comes to delivering ionization that's going to work correctly in the world that you need it to work in. So basically, we came up with this idea to really assist people to understand how their ionizers were working or are working in the highly sensitive world in the future. And as device sensitivities continue to grow, it'll be imperative for future ionizers to perform better, grow with the sensitivities, if you will, in terms of how it's delivering ionization, because static charge in and of itself isn't going to go away. If anything, it's going to be more problematic. With this current feedback system that we designed, we envision that we'll be able to achieve that balance. 25 or 30% of all ICs will be manufactured at 10 nanometers or below by 2021. And we're going to need ionizers that can safely eliminate charges of 5 volts and below to avoid future failures. And that ends this part of the presentation. I'm willing to handle some questions now, but we also, I would think, want to give you a short video on how the Ionmaster performs in real life that we've been able to put together, and I think will be very educational.
So John, would you like me to run through the first part of the questions that we have from some of the field?
Well, that's a question. Should I do it now or after the presentation? What do you think?
It's up to you.
All right. Well,
okay, so the first one is, are there any independent lab testing results for Ionmaster or any multi-lab round-robin testing?
There is not any lab testing per se yet. We are planning on sending it out to UL for approval. It has been put in the hands of customers for evaluation in terms of how it's performing in different real-life scenarios. I'm not sure we could actually find a lab that can do that for us, although we will explore that, but it will be a UL-approved device when it's finished. And if there is a lab out there that can, quantify its performance characteristics, we will certainly take that into consideration and have it evaluated from that perspective.
Okay. And then there's an interest in a three-dimensional ion decay mapping, which this individual thinks this may be possible with the device. Have there been any attempts at making this possible with Ionmaster?
There has not. It's not something we took into consideration. It's a possibility that we could incorporate in a future design, but right now that's not how we anticipate it being used.
What is the lowest balance voltage the Ionmaster can detect?
Right now, the lowest voltage balance that we can detect is roughly around 3 to 4 volts. And we anticipate enhancing that in the future with in-tool solution that we plan on coming out with later in the year. But for most applications, we feel that that's a very accurate solution for what customers are going to require.
Then how sensitive is the Ionmaster to ESD itself?
Not at all.
Okay. Do we, are there any units available for others to evaluate in the field?
There will be in the future. We have a couple out in a couple of customers' hands, and we expect to have a couple of other clients of ours that do some evaluation and performance on how the device works. So, yes.
And then what is the maximum balance voltage the system can measure and why?
Well, the maximum balance is set at plus or minus 30 volts, and the reason for that was due to certain regulatory low voltage requirements, which we would exceed if the combined voltage starts getting up above 60 or 65. And the other reason we went with that configuration was we're really trying to measure sensitivities. And we really think that, as the world is evolving below 35 volts in the standard, 30 volts was a pretty accurate and a pretty good number to start with. Because in a couple of years, people are going to need to be below that number, and that's what they really want to have confidence in.
The next person is assuming that this needs to be calibrated. How frequently does the equipment need to be calibrated? And if it does it go back to the NRD laboratory?
For the time being, it would come back to our laboratory. We would calibrate and quantify it and send it back. And we just need the sensor back to do that.
And it would be one time a year?
Once a year, yes.
Okay. And then does it function by power supply or a battery?
It derives its battery out of the tablet, so it operates on a battery concept. There's no individual power supply.
This next one, has anyone made a 1-inch CPM grid and then it goes into 10 by 10 to assess charging and dissipation distribution? So for example, on a scale of 300 millimeter wafer or photomask, since positive and negative ions do not travel at the same speed.
Not that I'm aware of.
Okay. Will the software for this device be available to load on devices other than the provided tablet?
Not initially, but there will be future reiterations where the software can be sold as a separate entity with the sensor for different applications. But for something that's going to be used to for current measurement purposes, it's a complete system: tablet, interface board, sensor.
And then how much will the product cost?
The 1-hour pricing is $4,200. Obviously, if people are buying multiple quantities of the device, there's quantity discounts to go with that.
Can the new sensor be made into 100 sensor array for mapping?
You could. And there's going to be a reiteration of this that would make a little bit more sense that we have planned for a future development later on this year. So it certainly is possible. And it also, we've got a system just conceptually where multiple sensors can feed information back to a central controller, and from the controller you can read out the data through a wireless interface. So that's all in the future plans. So you could have, if you wanted to, you could have 1,000 sensors hooked up around a plant with a controller and read all that data out throughout the entire facility back to one stationary location.
So the next one they've asked, I think it's a subset of the prior one though, is what will the result of measurement at a higher voltage stream of greater than 30 volts? So will the higher voltage damage the system?
The higher voltage won't damage the system. It'll just, when we're measuring it, we'll just show it as an out of range. Once you go beyond the 30 volts, it'll just go off the screen as it doesn't go off the screen, but it just goes out of range.
Okay. And when will the system be commercially available?
This quarter.
And is it going to be included on the ANSI ESD S3.1 approval?
We've presented this to the ESDA symposium group, and we plan on having another gathering later on this year to provide further information on how the sensor itself works. And we do hope that it gets incorporated into the next generation of testing methodologies that are used for ionizers to go along with the charge plate. But that will be, part of the committee's, understanding of how it operates. And I'm sure that they would like to incorporate this into their standards based on a presentation that I did with them last year. So I think for the most part, it's a matter of time on when that will occur. Once they fully understand what we're trying to do here conceptually, they realize what this device is capable of doing. So I fully expect that to occur.
So now that we have this measurement capability, have you been surprised at some of the testing results?
We have, and we, without getting too in detail, there's been a lot of interesting responses that we've seen from different platforms we've evaluated, as well as just some interesting things we've discovered with air movement, how ions perform along those lines.
Will this do a single charge nanoparticle detection?
If it's just a single nanoparticle positive or negative ion, we possibly could see it. It's really not designed to do that, but it would draw in one negative ion. We would probably not recognize it all that effectively, as we're looking for an air current of ions to measure against what a decay performance curve would look like. But in the future, if that was a need to measure something that not impactful, well, we could probably take a look at it, but that's really not the goal of what this device is designed to do.
Okay. So another question was about how the results are displayed, but that may be best to move into the video demo.
Yes.
Okay. So if you'll stop sharing your screen, I will bring in the video.
Yep.
Okay. Okay. And sorry for the delay here, but it's a larger video. It's only going to last for a few minutes. All right, here we go.
Hi, I'm Rob, one of the engineers here at NRD. I'm going to demonstrate how to use the Ionization Monitor Model 1000, the first of the Ionmaster family of ionization products. We're really excited about Ionmaster because we now have a method to measure the performance of our ionizers that's quick and nimble and easy to move from bench to bench. And it's the type of resolution you've been looking for. It works with all kinds of ionizers, not just the NRD ionizers. We're all familiar with the charge plate monitor, but it does pose some challenges. So it's nice to finally have an alternative to monitor ionization performance that avoids many of these potential issues. So let's see how the Ionmaster monitor works. The first thing you need to do is set up the Model 1000, is connect the cables and ground it like this. Next, you'll need to turn on your tablet, open the application, and allow it to warm up for approximately 10 minutes. If everything is connected properly, the launch screen will go away and you'll see your interface window. Now you're ready to start monitoring. To do this, just place the sensor in front of your ionizer with the arrow on the sensor as your guide for positioning. It should be placed perpendicular to the airflow, like this, with the sensor within 18 inches of your ionizer to ensure an accurate reading. That's important to remember because not all setups will look like this, over at ionizers for example. So, you always need to make sure you're pointing the sensor into the airflow. Keep in mind, the sensor needs to remain motionless while monitoring. Looking at the screen here, you can see you're able to view your monitoring information in two formats. We can just click here to toggle between the summary page and the XY axis graph. The summary page shows a 3-bar graph displayed in real time, balance, and decay rates. And the XY axis graph is another view of the same information. With Ionmaster, the max data range for ion balance is -30 to +30 volts, and the maximum upper decay time is 120 seconds. To change these limits, simply click on the number and enter your new value. The top right has the min and max values recorded during your session. To reset the values, just click on the Reset Min-Max Values on the summary page. Now watch what happens when I move the sensor like this. Ionmaster gives us the ability to move the sensor closer and further away from the ionizer to meet the established parameters that you have for measuring and monitoring the ionizer, all in real time. Just remember, after you locate the best distance, to keep the sensor motionless for a complete reading. Of course, if you want to ensure you always stay within these parameters, you can leave a monitor right at your workbench and detect issues in real time. Data is crucial. so it's important to have a way to save. To do that, just hit the Start Record button. The timer will count down for the amount of time data is being recorded, and then press Stop when you're finished. The longer you let the timer go, the more data points you can save. Upon reviewing the results, you can press Download, and this will save the data on your tablet as a CSV file using the standard Windows features. If you question the results, you can press Reset and start the process over again. If you're checking multiple ionizers, just do the same for each. Then you can transfer at one time all the saved CSV files to your company's system to track historical performance data. And that's it. It's all pretty intuitive, and I hope you found this helpful. And I really hope you like the IonMaster Ionization Monitor Model 1000.
And there you go. And John, I think you may want to, I don't know if you want to share your screen one more time.
So let's see, we're going back into this one.
Now the next two slides, if you go 2 slides down, then you will see the contact list that Ted has included.
No, I know, I'm trying to figure out why. So, oh, there we go.
And
That was the Ionmaster demo. I hope everybody enjoyed it. And for contact information, you can reach me at jglynn@nrdllc.com. My telephone number is located there as well. And for Ted Dangelmayer, you can reach Ted at his email address and his cell phone contact number as well. And I hope this was a very informative webinar for everybody involved in terms of where we think the world's going in terms of sensing ionization performance and giving people the tools to understand how to best monitor what's actually happening into their specific environments. Again, thank you very much for your time. Ted, thank you for setting this all up, and look forward to speaking to folks in the future.
And thank you all for joining us. Nice job, John. Appreciate it. And we look forward to having you join us on the next webinar.